FIFO Design Guide. This tutorial covers the complete flow from FIFO specification to SystemVerilog RTL implementation. Let's look at when to use FIFO. There are two use cases. First, data rate matching. When the producer is fast and consumer is slow. Consider this example. Here the CPU works at 100 MHz, but the UART transmitter can send data roughly 100 kilobits per second. Without FIFO, CPU should wait for a long time between each write operation. In this use case, FIFO acts as a buffer to a smooth data flow. Second use case, clock domain crossing. When the producer operates at clock domain A and consumer operates at clock domain B. Clock domain A and clock domain B are asynchronous. It means that there is no phase relationship between clock A and clock B. In this use case, FIFO acts as a data synchronizer and prevents metastability. In this tutorial, our focus is first use case, data rate matching. We plan to design synchronous FIFO. Let's look at FIFO specification. What is the key requirement? First, width and depth should be configurable, and depth must be power of 2. The FIFO has an asynchronous active low reset, which is usually used for ASIC design. Read and write operations are synchronous on clock rising edge. There are two flags, FIFO empty and FIFO full. What is the implementation strategy? We use array of register for storage. Also, we use separate read and write pointers. We need a register to store the last operation. When read and write address are equal, we use this register to determine the FIFO is full or empty. Consider this example. The read address points to this location. The reader module read from FIFO. So it read this location, this, and after some read, the read and write address point to the same location. Because the last operation was read, the FIFO is empty. Let's look at another example. The writer module write to the FIFO. Initially, the write address point to this location. Then it write to this location, wrap back to a start of the FIFO, and finally, the read and write address are equal. Because the last operation was write, the FIFO is full. It means that we need a register to store the last operation, and we use this information to determine that FIFO is full or empty. FIFO operation flow. First, look at write operation. Initially, the write address is set to 0. During the write operation, it checks if FIFO is not full. Then it stores data at current write address. So in this example, it stores data here. Then it increments the writer pointer. After that, the writer pointer points to this address. Now let's look at read operation. Initially, the read address is set to 0. During read operation, it checks if FIFO is not empty. Then it outputs data from current read address. So the data in this location, it goes to output. After that, the read address is incremented by 1. So here is the read pointer. Because the FIFO depth is a power of 2, when the write address or read address reach the end of the array, it wraps back to the beginning of the array. To determine FIFO flag, we look at the last operation. If the pointers are equal and the last operation was read, the FIFO empty is set. If the last operation was write, the FIFO full is set. This slide shows the write and read operation when the FIFO depth is 16. The writer module put the data to FIFO input. and then set the write enable. The writer can continuously write to FIFO. During the last write, the full flag is set to 1. It tells the writer module that this is the last write operation, and after that the FIFO ignore the write operation. Now let's look at the read operation. The reader module set the read enable to 1 and read data. It reads 16 data from the FIFO. During the last read, the empty flag is set to 1. It tells the read module that this is the last data inside the FIFO, and after that the read operation is ignored. Now let's look at the RTL code. We divided the FIFO module into different parts: parameters, ports, time scale, local parameters, local signals, register array, and function. First, declare parameters. We have two parameters, FIFO depth and data width. Here we define the parameters. Next, we declare the ports. We declare the clock and reset, write port and read port. Next, we declare signals. Time scale. We set the time unit to 1 nanosecond. To compute address width from the depth, we use SystemVerilog clog2 function. clog2 returns the ceiling of the logarithmic base 2. Let's look at some example. If depth is 8, clog2 of 8 is 3. It means that we need 3 bits to address 8 unique locations. If depth is 10, clog2 of 10 is 4. It means that we need 4 bits to address 10 unique locations. We use address width to declare read and write pointer. In this line, we use register array to declare memory, the memory width, and the depth. Now let's look at write operation. Here I copy the FIFO specification related to write operation. During the write operation, the write pointer is initially set to 0 in this line. During the write operation, we check if FIFO is not full. So it's write operation and FIFO is not full. We store data at current write address. Here's the input data and we store it in the current write address of the memory. Then we increment the write pointer. In this line, we increment the write pointer. We code the write operation inside a sequential block. Let's look at read operation. Initially, the read pointer is set to 0. During the read operation, we check if FIFO is not empty. Here is read operation and FIFO is not empty. Output data from current read address. Here is the current read address and we put it in the output. Then increment read pointer. In this line, we increment the read pointer. Track last operation. As we discussed earlier, we need a register to store the last operation. It called last was read register. Initially, the FIFO is empty, and we set the last was read to 1. If the last operation was read and FIFO is not empty, the last was read is set to 1. It means the last operation was read. If the last operation was write and FIFO was not full, the last was read is set to 0. It means that the last operation was write. Otherwise, the last operation preserves its previous value. Output flags. If write pointer is equal to read pointer and last operation was write, the FIFO is full. If write pointer is equal to read pointer and last operation was read, the FIFO is empty. And with that, we've completed the RTL code for our FIFO implementation. Now let's look at simulation waveform. The simulation is divided into two phases, write and read phase. Initially, the full flag is 0 and empty flag is 1 because FIFO is empty. Then we start to write to FIFO. We write 16 data. During the last write, the full flag is set to 1. It tells the writer module that this is the last data that can be written to FIFO. After that, the FIFO ignores the data because the FIFO is full. In second phase, we read from FIFO. The read enable is set to 1. We read 16 data from the FIFO. During the last read, the empty flag is set to 1 and it tells the reader module that this is the last data that can be read from FIFO. After that, the FIFO is empty. You can download the code for this tutorial in our GitHub repository. Thank you for watching this video.